Welcome back to Astronomy. We are in Chapter 15, Surveying the Stars. I believe that understanding stars is the most important thing in astronomy because a knowledge of stars and the patterns among stars and how stars operate helps us to understand galaxies. It helps us to understand the large-scale structure of the universe. And on the smaller level, it helps us to understand planets and the things that orbit around stars. So this is a very important chapter. And in this video, we're going to cover what is the most important diagram that helps us to understand stars, which is called the Hertzsprung-Russell diagram. So let's get into it. Patterns among stars. First, we'll do a quick review of the previous videos in Chapter 15. I want you to remember that stellar luminosity refers to the power emitted by a star. The higher the number, the brighter the star. We measure luminosity in solar luminosities, so how many times brighter than the sun it is. For example, the star Rigel, which is a very bright spring semester constellation, has 66,000 times the sun's luminosity. So therefore we say that it has 66,000 solar luminosities. Another bright star during the spring and summer is Sirius. In fact, it's the brightest star in the sky besides the sun. It is 25 solar luminosities. Now, I just said it's the brightest star in the sky, but you see Rigel is actually much, much brighter. And so this gets into the difference between what looks brighter to us and what is actually brighter. So Rigel is much brighter than Sirius. It's actually about 2,000 times brighter than Sirius. But when I say Sirius is the brightest star in the sky, that refers to how bright it looks to us. So both of the stars are much brighter than the sun, but Rigel has more than 2,000 times the luminosity of Sirius. We also learned about apparent magnitude, and I'll often abbreviate that and just call that magnitude. It refers to the brightness as seen from Earth. The lower the number of magnitude, the brighter the star looks to us. For example, the two stars I mentioned on the previous slide, Rigel has a magnitude of 0.12. Sirius has a magnitude of negative 1.46. So because Sirius's magnitude is lower than Rigel's, it looks brighter to us. And the reason is that it is much closer to Earth than Rigel is. Remember from the previous two videos of Chapter 15, astronomers classify stars based on two factors, luminosity and temperature. Part 1 video looked at stellar luminosities. Part 2 looked at stellar temperatures. And in this video, Part 3, we'll look at what we learn when we compare stellar luminosities and temperatures. I want to introduce you to the Hertzsprung-Russell diagram, or the HR diagram. The Danish astronomer Hertzsprung and American astronomer Russell independently, early in the 20th century, decided to make a graph of all the stellar data that they had, many, many thousands of stars, plotting their temperature versus luminosity to see what patterns they could find. So this is the Hertzsprung-Russell diagram, also known as the HR diagram. It plots luminosity and temperatures of stars. Most stars fall somewhere on what's called the main sequence of the HR diagram. So as Hertzsprung and Russell were making this graph, they found that 90% of stars fell on this diagonal line right here. Now, let's see what it means to be on this diagonal line. Remember that, as you can see, the horizontal axis is temperature and the vertical axis is luminosity. Let's look at that temperature axis first. This is different from most graphs that you've ever seen in that high temperatures to the left and low to the right. Usually we start left to right. We start with low numbers, usually at 0, going up to high numbers. But just the convention that Hertzsprung and Russell used And the way it fits in with how we classify stars, we do it high temperature to low temperature. So here you can see O stars are at and above 30,000 Kelvin, going into the coolest M stars a little less than 3,000 Kelvin. Luminosity, I want you to notice this is what's called a logarithmic scale, in that every increment on this vertical axis is multiplying by a factor of 10. So it doesn't go 10, 20, 30, 40, 50. That would be a linear scale, but it's logarithmic. So it's 1 and then multiplies by 10 to get 10, and then multiplies by another 10 to get 100 and 1,000 and 10,000 and 100,000 up to about 1,000,000 solar luminosities. So you have to be adept at scientific notation to be able to understand these axes. Notice right here at 1 solar luminosity, that means if I trace that 1 straight across anything that's at this level where my red dot is, that's going to be 1 solar luminosity. And there's the sun, right, where we expect it at 1 solar luminosity. We can also trace down with the sun, and it comes just a little cooler than 6,000 Kelvin, and you already knew that. The surface temperature of the sun is 5,800 Kelvin. You can also see overlaid on this horizontal axis with the temperatures is the spectral types, O, B, A, F, G, K, M. As we go down the graph in luminosity, we have 1/10 or 0.1. 10 to the negative 2 is 100th, 1,000th. 1/10,000th. So a 10,000th of a solar luminosity, that's about as dim as the dimmest stars get. Now let's look at this main sequence. I said that about 90% of stars are somewhere on the main sequence. So they are, there are these up here that are very hot. So they're to the left, meaning they're hot, and they're very high up, meaning bright. So very bright stars are very hot. And then we go down in temperature. We're also going down in luminosity. And that probably makes some intuitive sense that the brightest stars would be the hottest ones. And down here, the dimmest stars would be the coolest ones. And the sun is somewhere in the middle. It's about a medium temperature star and about a medium luminosity star. But then there are also the minority 10%. So here we have the main sequence, but then there are other stars. And this may have surprised Hertzsprung and Russell to see that some stars fell off of this main sequence. Stars with lower temperature and higher luminosity than the main sequence stars necessarily must have larger radii. They need to be bigger. And let's think why that is. If it's low temperature, every square meter of that star's surface is going to be relatively dim because of the low temperature. But these are very, very bright stars, stars that can be thousands or even hundreds of thousands times brighter than the sun. So if every square meter of this star's surface is relatively dim, it must mean it has a lot of square meters, meaning it has to be a very big star. So we classify these as giants and supergiants. So you notice where they fall in the Hertzsprung-Russell diagram. They are high and to the right. High means they are very bright. To the right means that they are cool temperature. Now, when I use phrases like cool temperature and high temperature, this is all relative because you can see this grouping right here are called supergiants. And let's look at this star right where my pointer is, this blue star right here. And I say it's cool, but it's blue. It's actually, as stars go, a very hot star. So maybe a better way to say it is that given its luminosity, it is a relatively cool star, because most stars of this luminosity are right here. They are O stars and B stars. But this star right here is an A star. So relative to stars that are this as bright as it is, it's a bit cooler. Now let's go down and to the left. Stars with higher temperature and lower luminosity than main sequence stars must have smaller radii. So here we have, let's take a look at this little star right here. And it is a very, very hot star. It's an O star, but it's very, very dim, only about between 10 to the negative 2 and 0.1 solar luminosities. So every square meter of this star, being how hot it is, close to 30,000 Kelvin, every square meter of that star's surface is very, very bright. And yet the total of the star is pretty dim. So that must mean it doesn't have too many square meters to it. It is a very small star. And they classified these as white dwarfs. This brings us to the stellar luminosity classes. Now you've already learned spectral types that are in the order of temperature, O, B, A, F, G, K, M. Separately, there are luminosity classes. A star's full classification includes its spectral type, which has to do with the identity of the emission lines and also the temperatures, and also what I'm introducing now, the luminosity class, related to the size of the star. Those go in sequence of Roman numerals, and I'll show this to you on the next slide, how it relates to the HR diagram. But they are Roman numeral 1, supergiants. So class 1 are supergiants, class 2 are bright giants, class 3 are giants, class 4 are subgiants, class 5 are main sequence. That's where the Roman numerals end. And then there are white dwarfs. We don't call them class 6, we just call them class D. And the reason for that is, as we'll find later on in this unit on stars, white dwarfs are not actually stars. They look a lot like stars, but for reasons we'll get into later, they are not actually stars. So astronomers just decided not to call them class 6, but rather just class D. So there's some examples written on this slide, but I'm actually going to go to the next slide to show those examples in the on the Hertzsprung-Russell diagram. So here we have these different classes, and it's easy to remember them because they just start at the upper right of the HR diagram and then go diagonally down and to the left. So at the far upper right are the class 1s, the supergiants. Now remember what it means to be at the far upper right. To be far up means very bright, and to be far to the right means very cool. So those are the supergiants, the coolest and brightest stars. And then we come down a bit, and that's actually going to be a reduction in size of the stars. We have the bright giants, class 2. The giants are class 3s. The subgiants are class 4s. And the main sequence are class 5 that are all along this line. And then we have the D-class stars, which are the white dwarfs. I also want you to notice, while we're looking at the Hertzsprung-Russell diagram, I've related this to the size of the stars. It's a little harder to see, but notice these gray diagonal lines that go from upper left to lower right. So right here, this gray line, it says 1 solar radius. So any star that's going to fall on this gray diagonal line is going to be the size of the sun, 1 times the radius of the sun. And there it is right there, the sun's sitting there. And then you go up to this gray line and it says 10 solar radii. So anything that falls on this line is going to be 10 times the size of the sun. And then we have 100 solar radii. Then we get into the realm of the supergiants, 1,000 solar radii. So any star along this line is 1,000 times the radius of the sun. We also get into the smaller stars, 0.1 solar radius, 0.01 solar radius, and 0.001, it says 10 to the negative 3 in scientific notation. So any star along this line is going to be only 1,000th the size of the sun. Let's get into those examples that I mentioned a couple of slides ago. Let's look at Betelgeuse right here. It is a spectral type M2 star. And now with these luminosity classes that I've introduced, it's a supergiant, so it's a class 1. So we can say that Betelgeuse is an M2 one star. Another example is the sun. There it is among the G's. So there's G, we trace it up. You know that the sun is a G2 star and it's class 5. So the sun is a G2 5 star. Again, the 5 meaning it's a main sequence star. And another main sequence star, this example right here, Sirius. It's a spectral type A1, and there it is. It's among those whitish blue stars. It's an A and class 5. So Sirius is a spectral type A1 5 star. So we can learn so much from the Hertzsprung-Russell diagram. It depicts the temperature. That's a measure of how much left to right the star is. Color, because remember, color goes along with temperature. We have red, orange, yellow, white, and blue. The spectral type, which goes along with the colors and the temperatures, it shows us the luminosity, so how high up and down it is the luminosity, and the radius, that's those diagonal gray lines there. Just as a quick review, I want you to think which of these stars, I've labeled 4 of them, A, B, C, and D, is the hottest. And so to discern which one is the hottest, I want you to remember that temperature goes left to right, and the left is the hottest. So we're just going to look for the leftmost star. And of the ones I've labeled, A, B, C, and D, A is the hottest star. Which star is the most luminous? And to discern which one is the most luminous, remember luminosity is how high up or down it is. And so the higher up, the more luminous. So it's going to be star C. Which star is a main sequence star? And I want you to remember the different classes of stars. We've got up and to the right, the supergiants, the bright giants, the subgiants, and anything along this diagonal line is a main sequence star. So D. Which star has the largest radius? And so we remember these gray diagonal lines, 0.01, 0.1, 1. So we're looking for, as we go up and to the right, seeing the scale of these gray lines, which one is the biggest, and so star C. I encourage you, if you had any problems with those last couple of questions I've just asked, picking which star A, B, C, and D, go back and review this entire video, what I've covered so far in the past roughly 17 minutes, because this is essential to understanding the rest of the unit on stars. And now let's get into it, the significance of the main sequence. Main sequence stars are fusing hydrogen into helium in their cores, just as the sun does. So that is going to be our important definition, our distinction. What is it about main sequence stars that makes them different from the giants, the subgiants, the white dwarfs? What is going on physically with them? And it's this: they are fusing hydrogen into helium in their cores. Luminous main sequence stars are hot, and less luminous ones are cooler. So we have the blues, the whites, the yellows. We get into cooler, dimmer ones, orange and red. We can measure the masses of main sequence stars. A lot of that comes from their orbital properties when they're in orbit around other stars. And it shows that hot blue stars are much more massive than cool red ones. So you notice now these purple letters and numbers here. Up and to the left, the hottest, brightest ones, they can be 10 solar masses, 30 solar masses, 60 solar masses, and on up even past 100. And then as you go down and to the right, so we go to the dimmer and cooler stars, there's the sun at 1 solar mass. And then we get into pretty much the lightest stars are about 1/10 of a solar mass, so 1/10 the mass of the sun. But so I want you to remember this now as you're thinking about the Hertzsprung-Russell diagram. On the main sequence, up and to the left, these hotter stars are the most massive ones. Down and to the right, these dimmer, cooler stars are the least massive ones. The mass of a hydrogen fusing star determines its luminosity and its spectral type. So when the star forms originally, when it's a newborn star, how much mass it has determines where it's going to be. If it has a lot of mass, it's just going to automatically become very hot and very bright. A low mass is going to automatically become very dim and very cool. And we will talk more about that in chapter 16 on the birth of stars. Getting into the physical processes that determine where it falls on the Hertzsprung-Russell diagram, the core's pressure and temperature of a high mass star needs to be larger in order to balance gravity. So if it's got a lot of mass, it's got a lot of gravity pulling it in, and there needs to be a higher temperature for a higher rate of nuclear fusion that's going to push out against gravity. The higher core temperature boosts the fusion rate, leading to a larger luminosity. I want to now point out to you this green wording and lettering, the lifetime of stars. Astronomers have been able to determine how long a star will live. And when we say live, not referring to biological life, but there is this recognition that stars go through a cycle. They are born, they become stars from a cloud of gas, and they go through these life stages, and eventually they cease to become stars. And so when we refer to the lifetime of a star, we're referring to its main sequence lifetime, how long it spends on the main sequence before it ceases to fuse hydrogen into helium in its core, and then at that point it'll go on to be a giant or a supergiant star. So we're looking at the main sequence lifetime, and this is based on the size of the star, so how much mass it has, how much fuel it has for nuclear fusion, and the rate at which it produces power. So we can determine the lifetime of stars. I want you to notice that as we start up here on the upper left, these high mass stars, 20, 30 solar masses, it's a lifetime of 10 to the 7th years, 10 million years. But as we go down to lower mass stars, it becomes a longer lifetime. So 10 to the 8th, that's 100 billion years. 10 to the 9th, 10 to the 8th is 100 million years. 10 to the 9th is a billion years. We go to these lower than the sun mass stars. Actually, right here is the sun, 1 solar mass. 10 to the 10th, that's 10 billion years. Then the even lower mass stars, 10 to the 11th, 100 billion years. And it's not written on this slide, but the lowest mass stars can be 10 to the 12th, or 1 trillion years. Now it seems counterintuitive that the stars that are the largest, they have the most mass, that they would have the shortest lifetimes. So why is it that if they have the most mass, the most fuel for hydrogen fusion, why would they live the shortest amount of time? And there is an analogy here to automobiles. So I want you to think of these high mass stars as the gas guzzlers, like this pickup truck. Now, a pickup truck like this will have very low miles per gallon, meaning it burns through a lot of fuel very quickly. And it's got a very large gas tank. So if you just think about the very large fuel tank on these trucks, you think, well, it should be able to drive for a long time, a long distance because of the large fuel tank. But you have to balance that with the fact that it's not very energy efficient. It burns through that fuel very quickly. That's what these high mass stars are doing. So you take a star that is about where my pointer is, and maybe it's about 10 times the mass of the sun. So it's got 10 times the fuel tank that the sun has. 10 times the fuel tank, 10 times the amount of hydrogen to burn. You have to now balance that with, if you go over to the left on the luminosity scale, it's 10,000, maybe even 100,000 times more power that it puts out, meaning it's burning at least 10,000 times faster than the sun is. So it's got 10 times the hydrogen fuel, but it's burning it at a rate more than 10,000 times faster. So it's going to burn out more quickly. You can contrast that with these low mass stars that might live 100 billion or even a trillion years. And those are like this fuel-efficient Toyota Corolla. It's got a small gas tank, but it's very fuel efficient, so it doesn't burn through the fuel very quickly. And that's what these red stars are doing. You look at a star like about right where my pointer is, a red star like this, 1/10 of the mass of the sun, meaning it's only got about 1/10 of the hydrogen to burn. But let's go over to the left of the scale, 1/100th, maybe even 1,000th the rate of power that that's the rate that it's burning through that fuel. And so if it's only 1,000th the brightness of the sun, it's only burning through the fuel at 1,000th of the rate. And so it's going to live a lot longer than the sun does. Let's put all this together and think of the ranges of stellar properties. The ranges of luminosities, and we learn this from the brightness of a star, how bright it looks in our sky, and its distance, and we can discern the luminosities. And the range is, let's look at the non-bold print letters here, from between 10 to the -4 solar luminosities and 10 to the 6th solar luminosities. So between 1/10,000th the brightness of the sun and about 1,000,000 times the brightness of the sun. Now, over here I've written how this relates to the masses of stars. The dimmest stars are about 0.08 times the mass of the sun. And we'll get into in chapter 16, the birth of stars, why that's the low end of masses of stars. The brightest stars are about 100 times the mass of the sun. Now, we don't know exactly how massive a star can be. Computer models suggest about 100 times the mass of the sun is about as massive as it's going to get, although we think we've seen stars that are maybe as much as 200 times the mass of the sun. Temperature ranges. The coolest ones are the M stars, about 3,000 Kelvin, to the hottest ones, the O stars, about 50,000 Kelvin. And again, this correlates to the masses of the stars. The cool ones are going to be those lowest mass stars of about 0.08 solar masses, and the hottest ones are going to be something like about 100 solar masses. We learn the mass of stars from the orbital properties of stars that are in binary orbits. So the period of the stars, how much it takes them to go around each other, and their average separation. And we have discerned that the lowest mass stars are 0.08 solar masses. The highest mass, we're not sure because high mass stars are rare, so we don't have as much data, but somewhere in the ballpark of about 100 solar masses, maybe as much as 200 solar masses. As we think about the range of just main sequence stars, the highest mass stars, and think on the Hertzsprung-Russell diagram, that's going to be up and to the left. They're the brightest, they live the shortest amount of time, they're the largest, and they are blue. So stars like Spica right here. It's a B1 main sequence star. It's about 11 solar masses, and it is a lifetime of only about 10 to the 7th years. We move on down to the lowest mass main sequence stars, something like Proxima Centauri here, which happens to be the closest star to the sun. It's about 4.2 light years away. These are the lowest luminosity. They live the longest, they're the smallest, and they're red. So Proxima Centauri is an M. It says here M5.5. I'm not interested in you getting into the nuances of these decimal spectral types. I don't want to complicate things even more. I've taught you that they are integers, so there's M5s and M6s, but on this chart it says Proxima Centauri is an M5.5, so that's just getting more specific. It's somewhere between an M5 and an M6. Class 5 means it's a main sequence star. It's got a mass of only 0.12 solar masses, and it's a lifetime of about 1 trillion years. And here we have a size comparison just of main sequence stars. Now you get into the giants and the supergiants, and they will be much bigger than these right here, but just gives you a nice size comparison. So a G star like our sun, right about there, and you can see those comparisons. And in the next video, we'll get into the other types of stars, giants, supergiants, and white dwarfs.